They finally saw it. After months of tracking 3I Atlas through its violent encounter with the Sun, the Hubble Space Telescope stripped away the glowing haze and revealed the core. What came back wasn't just unexpected. It was impossible. A nucleus 27 times more massive than every prediction. But here's where it gets unsettling. That was the least strange thing about it. Methane is appearing when physics says it should be long gone. Metal ratios are matching industrial processes, not natural ice. And this massive object is changing course in ways its own weight shouldn't allow. 4 independent measurements. 4 separate contradictions. One visitor from another star system that's rewriting the rules. Tonight, we're walking through every anomaly, every failed explanation, and the one question no one wants to ask out loud. Stay with me until the end. Because what 3I Atlas is revealing might be far bigger than the comet itself. Subscribe and follow along, because the story of 3I Atlas isn't over, and neither is the larger mystery it represents. More interstellar visitors are coming. They're already out there, drifting through the void, headed toward our solar system. We can't predict when they'll arrive or what they'll reveal. But if 3I Atlas taught us anything, it's that every assumption we make gets tested when objects from other star systems show up. Scientists thought the story was mostly over. Comet 3I Atlas had survived its brutal swing around the Sun in January 2025, bled gas and dust across the inner solar system, and was now fading into the cosmic background like every other comet before it. The telescopes would track it for a few more months, catalog the data, and move on. That was the plan. The observation schedule was winding down. Researchers were already drafting their preliminary papers. The narrative seemed complete. Another interstellar visitor had come and gone, leaving behind a trail of measurements and a few interesting quirks, but nothing that would fundamentally challenge our understanding. But then Hubble looked closer. Between December 2025 and January 2026, the Hubble Space Telescope turned its instruments toward the retreating comet and did something astronomers had been attempting for months. It isolated the nucleus. Not the glowing cloud of gas around it. Not the vast tail streaming millions of kilometers behind it. Just the solid, icy body at the center. The actual object itself, stripped of all the theatrical display. To do this, astronomers painstakingly subtracted the brightness of the coma, the fuzzy halo of evaporating material, from the total light signature. This is delicate work. The coma is thousands of times brighter than the nucleus. Separating the two requires precision. It requires multiple observations. It requires careful calibration and mathematical modeling. But when the process was complete, what remained was the nucleus itself, naked and measurable. This wasn't inference. This wasn't a model prediction based on activity levels or brightness fluctuations. This was a direct measurement of the thing itself. The core of 3I Atlas laid bare for the first time. The number that came back detonated every expectation they had built over the previous year. The effective diameter of the nucleus measured 2.6 kilometers, plus or minus 0.4 kilometers. To put that in perspective, that's roughly the length of 30 football fields laid end to end. That measurement assumed an albedo, a surface reflectivity, of 0.04, which is standard for cometary bodies. These objects are dark. They're coated in organic compounds that have been irradiated by cosmic rays for millions or billions of years. They reflect almost nothing. So when you see light coming off them, you know the size has to be substantial to account for that brightness. 2.6 kilometers. That number landed like a bomb in the astronomy community. Before perihelion, before the comet had even approached the Sun, the scientific consensus hovered around 1 kilometer, maybe slightly larger, maybe slightly smaller. Some optimistic estimates pushed it to 1.2 kilometers. But the models, built on observations of brightness and activity, all pointed to a modestly sized interstellar snowball, something fragile, something fluffy, something that might not even survive the intense solar heating. The pre-perihelion discussions centered on whether the comet would fragment, whether it would hold together, whether we'd witness a catastrophic breakup in real time. 2.6 kilometers was not modest, it was massive. It implied a mass increase of roughly 27 times what had been predicted. And in astrophysics, mass is everything. Mass determines gravity, thermal inertia, structural stability, and orbital dynamics. Mass is the variable that governs how objects behave. Size matters, but mass matters more. When you double the diameter of a spherical object, you don't double its mass. You multiply it by 8. Mass scales with the cube of diameter. So even small errors in size estimation translate into enormous errors in physical consequences. A comet twice as wide is 8 times as massive. A comet 2.6 times as wide compared to 1 kilometer is roughly 17 times as massive in linear terms. But when you account for density variations and the actual volume increase, you end up with that factor of 27. A 2.6 kilometer nucleus doesn't just look different. It behaves differently. It moves differently. It outgasses differently. It survives solar heating differently. It exists differently. And suddenly, everything astronomers thought they understood about this object was fundamentally wrong. Let's put this in context, because context matters when you're trying to grasp just how unprecedented this is. Oumuamua, the first confirmed interstellar visitor, measured less than 0.2 kilometers across. Some estimates put it as small as 100 meters. It was effectively dust scale compared to this. It was a shard, a fragment, barely larger than a city block. 2I/Borisov, the second interstellar object and the first confirmed interstellar comet, came in around 0.7 kilometers. Respectable, but still small. Still within the range of what we expect from typical comets. 3I Atlas is the heavyweight. It's not just larger. It's not just at the upper end of the distribution. It's orders of magnitude more massive than either of its predecessors. And that creates a psychological whiplash that's hard to overstate. Scientists had spent months preparing for a fragile object. The models predicted low density, high porosity, a structure more like a snowbank than a solid rock. Something that might fragment under stress. Something that would barely survive perihelion, the closest approach to the sun, where temperatures spike and thermal gradients can tear objects apart. Instead, they found a dense, kilometer-scale body that not only survived, but seemed almost indifferent to the sun's brutality. The comet didn't fragment. It didn't split. It didn't show any signs of catastrophic structural failure. It just kept going, shedding gas and dust at rates consistent with a massive, thermally stable object. This wasn't what interstellar visitors were supposed to look like. This wasn't what the models predicted. This wasn't what anyone expected. And here's the kicker, the detail that removes any remaining doubt. This size wasn't just measured by Hubble. It was independently supported by calculations based on outgassing rates and the rocket effect, the subtle push a comet experiences as gas jets off its surface. Those calculations, built on entirely different data sets, using entirely different methodologies, pointed to the same conclusion. The nucleus had to be large. Multiple lines of evidence converged. The numbers piled up. There was no escaping it. This wasn't a measurement error. This wasn't a calibration issue. This was real. So now astronomers faced a problem. If the nucleus is really this large, if it's really this massive, then the motion should behave differently. The chemistry should behave differently. The statistics of finding such an object should behave differently. But here's the thing, they don't. The motion is wrong. The chemistry is wrong. The statistics are wrong. Every independent line of evidence is misbehaving in its own unique way, refusing to align with the new mass estimate. And that's where the math stops cooperating. A comet isn't just a ball of ice drifting through space on a predictable trajectory. It's an engine, a self-propelled object that changes its own orbit through the simple act of existing. As it approaches the sun, solar radiation heats its surface, pouring energy into the frozen volatiles locked in the ice. That heat turns ice directly into gas without melting at first, a process called sublimation. The gas escapes, often in concentrated jets shooting from specific locations on the surface, and in doing so, it pushes. It exerts force. It imparts momentum. This is called non-gravitational acceleration. It's a subtle effect, typically small compared to the gravitational forces from the sun and planets, but it's measurable. And for 3I Atlas, it became a massive problem, a fundamental contradiction that refuses to resolve. Astronomers observed that 3I Atlas deviated from its predicted trajectory. They calculated where the comet should be based purely on gravitational interactions, the Newtonian mechanics that govern every object in the solar system. They accounted for the sun's pull, Jupiter's influence, the minor perturbations from other planets. And when they compared those predictions to where the comet actually was, they found a discrepancy. Gravity alone, the combined pull of the sun and planets, could not explain where the comet ended up. Something was pushing it. Something was altering its path in ways that gravity couldn't account for. That something was the rocket effect. Gas jetting off the surface was changing the comet's trajectory, accelerating it in directions that pure orbital mechanics couldn't predict. This is normal. This is expected. Comets do this all the time. What's not normal is how much it moved, given how massive it now appeared to be. Two researchers, Forbes and Butler, analyzed the observed acceleration and combined it with plausible estimates of how much mass the comet was losing through outgassing. They looked at the brightness of the coma, the density of the gas cloud, the rate at which material was being expelled. From that, they could estimate the thrust, the force being generated by the escaping gas. And from the thrust and the observed acceleration, they could derive the mass of the nucleus. It's basic physics. Force equals mass times acceleration. Rearrange that equation, and you can solve for mass if you know the other two variables. Their goal was to derive the size of the nucleus required to produce the observed motion. The answer they got was 0.8 to 1.1 kilometers. Reasonable. Expected. Consistent with what everyone thought before Hubble took its measurement. And then Hubble said 2.6 kilometers. Let's be absolutely clear about what this means. The observed acceleration implies a certain nucleus size. The observed brightness implies a completely different nucleus size. And those two numbers are separated by a factor of roughly 27 in mass. That's not a small discrepancy. That's not a rounding error. That's not something you can explain away with a minor adjustment to your model parameters. That's a physics problem. That's a situation where two independent lines of evidence are giving you contradictory answers, and both lines of evidence are based on solid observational data. Acceleration equals force divided by mass. This is Newton's second law, one of the most fundamental equations in physics. If you increase the mass of an object but keep the force the same, the acceleration decreases. It has to. There's no way around it. A heavier object should move less, not more. A car with a small engine accelerates quickly. The same engine in a truck barely gets the vehicle moving. But 3I Atlas is moving more than it should. It's accelerating as if it's light, as if it's a small, fluffy snowball being pushed around by modest outgassing. But it's shining as if it's heavy, as if it's a massive, solid body with substantial surface area. Both things cannot be true at the same time, unless something fundamental in our understanding is incomplete. Scientists have proposed fixes, workarounds, adjustments to make the numbers align. Maybe the jets are stronger than expected. Maybe the outgassing is far more vigorous than standard models predict. Maybe the comet is expelling gas at rates that dwarf what we've seen in solar system comets. That could work mathematically. If you increase the force term in the equation, you can keep the acceleration high, even with a large mass. But there's a problem: energy. A comet only has so much thermal energy to work with. It gets heated by the sun, and that heat drives sublimation. You can't just dial up the outgassing arbitrarily without violating the energy budget. The sun only delivers so much power per square meter of surface. The comet can only absorb so much of that energy, and it can only convert so much of that absorbed energy into the latent heat of sublimation, the energy required to turn ice into gas. The math has limits. The physics has constraints. You can't simply wish for more vigorous outgassing without explaining where the extra energy comes from. Maybe the jets are highly focused. Instead of gas escaping evenly across the surface, maybe it's concentrated into narrow, powerful streams that maximize thrust. Imagine the difference between a garden hose spraying wide and a pressure washer concentrating the same water flow into a tight beam. The pressure washer pushes harder. That could work here. If the jets on 3I Atlas are unusually narrow, unusually concentrated, they could generate more thrust per unit of mass lost. But it requires extreme geometry. The jets would need to be aimed almost perfectly to generate the observed acceleration in the observed direction. And we've never seen evidence of such precise jet alignment in any comet, interstellar or otherwise. Solar system comets have jets, certainly, but they're typically broad, diffuse, and oriented in multiple directions. The net thrust is modest. Getting a large net acceleration would require very specific conditions. It's possible, but it's convenient. And in science, convenience is not an explanation. Convenient answers are often wrong answers, dressed up to look plausible. Maybe the outgassing is time-lagged. Maybe heat penetrates the nucleus slowly, diffusing through the icy matrix over hours or days, and gas is released hours or even days after peak solar heating. This can create asymmetric forces that alter the orbit. When the comet is closest to the sun, it's not outgassing most vigorously. Instead, maximum outgassing happens later, after the heat has had time to penetrate. This shifts the direction of the thrust, creating orbital changes that differ from what you'd predict with instantaneous sublimation. Time-lagged outgassing is a known phenomenon. We've observed it in solar system comets. It helps explain certain orbital peculiarities. It helps, but even accounting for it, the numbers don't quite close. Even with optimal time lag parameters, even with the most favorable assumptions, the object is still moving too much for its size. The discrepancy shrinks but doesn't disappear. So astronomers are stuck with an uncomfortable fork in the road. Either the nucleus size is wrong, and Hubble's measurement is somehow off by a factor of 3, which would require a systematic error of unprecedented magnitude in one of the most reliable instruments in astronomy. Or the acceleration model is incomplete, and we're missing a fundamental piece of how these objects respond to solar heating, which would mean decades of cometary physics need to be revised. Or outgassing physics behaves differently in interstellar objects than it does in solar system comets, and we have no idea why, which would suggest that our entire baseline for understanding comets is parochial and limited. All 3 explanations undermine frameworks that have worked for decades. All 3 are deeply unsettling. All 3 force scientists to question assumptions they thought were solid. And just as scientists tried to patch this, to find some clever way to reconcile motion with mass, to develop a model that could accommodate both the brightness and the acceleration, the chemistry refused to cooperate. Because what came next didn't just violate models, it violated thermodynamics itself. On December 15th and 16th, and again on December 27th, 2025, the James Webb Space Telescope pointed its MIRI spectrometer at 3I Atlas. MIRI, the mid-infrared instrument, is designed to detect infrared light, the kind of light emitted by molecules as they vibrate and rotate in space. Every molecule has a unique set of vibrational modes, a unique way of absorbing and emitting infrared radiation. It's like a fingerprint. You can identify specific chemicals based on their spectral signatures, the wavelengths at which they absorb or emit light. MIRI is phenomenally sensitive. It can detect trace amounts of chemicals in the thin, cold environments of space. And when the data came back from those December observations, astronomers found something that shouldn't have been there: methane. Methane was present in the comet's coma, mixed with water vapor and other gases, glowing faintly in the infrared as solar radiation excited its molecular bonds. That's unusual, but not shocking. Comets can contain methane. We've detected it before in solar system comets, though typically in small amounts. What's shocking is when it appeared and how much of it there was. In the first observation epoch, December 15th and 16th, methane accounted for 13.7% of the water production rate. That's a substantial fraction. That's not a trace detection. That's a major volatile component. By the second epoch, December 27th, that fraction had jumped to 27%. Methane was increasing. Methane was becoming more prominent as the comet receded from the sun, and that is completely backward. Methane is one of the most volatile substances in a comet. It's a simple molecule, 4 hydrogen atoms bonded to a single carbon atom. It's light. It's weakly bound. It sublimates, transitions directly from ice to gas at much lower temperatures than carbon dioxide and far lower than water. Methane ice starts sublimating at around 50 Kelvin, negative 223 Celsius. Carbon dioxide requires about 150 Kelvin. Water ice doesn't sublimate significantly until you reach 200 Kelvin or higher. In any reasonable thermal model, methane should erupt first. It should vent early, long before the comet gets close to the sun, back when the object is still in the cold outer reaches of the solar system. And it should be gone by the time water dominates. Water ice is stubborn. It holds on longer. It requires more heat. By the time a comet is spewing water at high rates, by the time it's close enough to the sun for water sublimation to be vigorous, methane should have already vanished weeks or months earlier. But here's the contradiction, the observation that makes no thermodynamic sense. No methane was detected in August 2025, months before perihelion, when the comet was still relatively cold, still far from the sun, still in the temperature regime where methane should be most active. Carbon monoxide and carbon dioxide were detected then. Both are volatile. Both sublimate at low temperatures. Carbon monoxide is even more volatile than methane, sublimating at around 25 Kelvin. If any volatile should have been present in August, it should have been methane. But it wasn't. The spectra showed carbon monoxide. They showed carbon dioxide. They showed no methane. And then, post-perihelion, when the comet should be depleted of its lightest ices, when months of solar heating should have baked off everything volatile, methane shows up. Not faintly, not as a trace, but at percentages that rival or exceed the earlier volatiles. It's appearing when it should be gone. The standard explanation, the go-to mechanism for unusual sublimation sequences, would be that methane was buried deep inside the nucleus, trapped beneath layers of less volatile ices like carbon dioxide and water. Picture the nucleus as an onion with different layers of ice at different depths. The outer layers sublimate first, exposing deeper material as the comet approaches the sun. As the outer layers of carbon dioxide and water sublimated away, deeper material became exposed, and methane finally reached the surface where it could escape. That's plausible. That's exactly how layered sublimation works. We've observed this process in solar system comets. Volatiles trapped beneath refractory crusts suddenly vent when fresh ice is exposed. Except it doesn't work here. It can't work here. And the reason why reveals just how broken the chemistry has become. Carbon monoxide is more volatile than methane. It sublimates at even lower temperatures. It's the most volatile major component in any comet. If methane was buried beneath a layer of carbon dioxide or water ice, then carbon monoxide should have been buried even deeper, because it would have sublimated away first during the comet's formation, or during previous stellar encounters. But carbon monoxide was detected early. It was present in August when the comet was still far from the Sun. It was outgassing vigorously during the pre-perihelion phase. So if carbon monoxide reached the surface early, if it was escaping months before perihelion, then methane should have reached the surface earlier. The sequence doesn't fit. You can't have carbon monoxide escaping early and methane appearing late if they're both buried in a stratified ice structure. The volatility ordering is wrong. The timeline is wrong. The mechanism fails. There is no internally consistent sublimation sequence that explains this. You can't have carbon monoxide appearing before methane if they're both buried and releasing according to standard thermal models. You can't have methane increasing post-perihelion if it's supposed to be the first volatile to escape. Something is producing methane, or storing it, or releasing it in a way that doesn't follow the thermodynamic rules we've relied on for decades. Either methane is being generated by an unknown mechanism inside the comet, perhaps through chemical reactions we've never observed, radiolysis processes that create methane from more complex organic molecules, or some exotic chemistry driven by cosmic ray bombardment. Or we're fundamentally misunderstanding how these objects store and release volatiles, which would mean our models of cometary structure and thermal evolution are missing critical physics. Neither explanation is satisfying. Both are troubling. And methane wasn't the only chemical that raised eyebrows. Because when scientists started examining the metal content, they found something even stranger. Comets are dirty snowballs. Everyone knows this. It's the standard description, the simplified model that conveys the basic composition without getting bogged down in details. They're made of ice and rock and organic compounds, leftovers from the formation of planetary systems, material that never got incorporated into planets. They're not supposed to be metallic. They're not supposed to have significant metal content. You expect silicates, carbon compounds, water ice, frozen gases. You don't expect iron and nickel in any substantial quantity. But 3I Atlas kept defying expectations. Nickel was detected consistently throughout the comet's activity, showing up in spectroscopic observations both before and after perihelion. Iron appeared post-perihelion, showing up in the data as the comet pulled away from the Sun, likely liberated from dust grains as intense solar heating vaporized the surrounding material. Metals in comets are unusual, but not unheard of. Trace amounts of iron and nickel can be locked into the rocky component, the non-volatile fraction that forms the structural framework of the nucleus. But what's unprecedented here isn't the presence of metals, it's the ratio. The nickel to iron ratio observed in 3I Atlas falls outside the range of every known solar system comet, not at the edge of the distribution, not in the tail of the bell curve, outside it entirely. This isn't a minor deviation. This isn't a comet with slightly more nickel than average. This is a signature that has no natural precedent in our astronomical catalog. Solar system comets show a fairly narrow range of nickel to iron ratios, consistent with the bulk composition of the solar nebula, the cloud of gas and dust from which the Sun and planets formed. That ratio reflects the relative abundances of these elements in the primordial material. It's universal across asteroids, meteorites, and comets. It's one of those constants that you take for granted, until it's not constant anymore. And when scientists tried to find analogs, when they searched through databases looking for anything with a similar nickel to iron signature, they found something uncomfortable. Similar ratios appear in industrial processes, specifically in certain high-temperature metallurgical environments where metals are refined, processed, separated, blast furnaces, smelting operations, certain types of alloy production. The ratio doesn't match natural ores. It doesn't match meteorites. It matches refined materials. Let's be absolutely clear about what this does and does not mean. This is not a claim of artificial origin. There is no evidence of construction. There is no evidence of intent. There is no suggestion that 3I Atlas was built by anyone or anything. No one is claiming this is an alien artifact. No one is suggesting extraterrestrial engineering. But the ratio itself, the specific balance between nickel and iron, matches what you'd see in certain human industrial contexts. That's context. That's comparison. That's a data point. And it's deeply strange because we have no natural mechanism that produces this ratio in a comet. Natural mechanisms can produce a wide range of elemental ratios. Stars forge elements through fusion, fusing hydrogen into helium, helium into carbon and oxygen, building up heavier elements through successive nuclear reactions. Supernovae scatter them across space, creating shockwaves that compress and heat material, triggering nucleosynthesis that produces even heavier elements. Planetary formation processes sort and concentrate them, with differentiation separating metals from silicates, and volatile loss altering the bulk composition. We have examples of nearly every imaginable chemical composition somewhere in the universe. High metal asteroids, carbon-rich meteorites, ice-dominated comets. But this specific nickel-to-iron ratio, in this specific context, in a comet, we've never observed it naturally. And that's the problem. Science relies on precedent. We understand phenomena by comparing them to things we've seen before. When something has no precedent, when it exists in isolation without analogs, we don't know what it means. We don't know if it's significant or trivial. We don't know if it points to new physics or just reflects the limited diversity of our sample. This is another independent line of evidence misbehaving. The mass was wrong. The motion was wrong. The methane was wrong. Now, the chemistry is wrong. Each anomaly, taken alone, could be explained. A measurement error here, an unusual thermal process there, a rare composition elsewhere, statistical noise, calibration issues, instrumental artifacts. But together, they resist closure. Together, they form a pattern. And at this point, coincidence starts feeling expensive. At some point, you have to ask whether these are really independent anomalies, or whether they're symptoms of a deeper misunderstanding. Scientists ask themselves, how likely was it to find this object at all? And that question led to the most unsettling anomaly of all. In astronomy, small objects outnumber large ones. This is true everywhere. This is universal. Asteroids follow this rule. For every kilometer-sized asteroid in the main belt, there are thousands of 100-meter asteroids. Comets follow this rule. Small, short-period comets vastly outnumber the large, spectacular ones. Exoplanets follow this rule. Small, rocky planets are more common than gas giants. Stars follow this rule. Red dwarfs outnumber sun-like stars, which outnumber massive blue giants. The universe follows a power law. For every big thing, there are many more small things. This isn't a suggestion. This isn't a trend. This is statistics. This is how populations work when formation processes are stochastic. When objects grow through accretion or fragmentation, when physics doesn't favor any particular size. Now apply that to interstellar objects. We've confirmed 3, Oumuamua, 2, I/Borisov, and 3I Atlas. 3 objects total. That's our entire confirmed population. One of them, Oumuamua, is less than 0.2 kilometers. Some estimates put it as small as 100 meters, the size of a football field. One is 0.7 kilometers. 2 I/Borisov, a respectable mid-sized comet. One is 2.6 kilometers. 3I Atlas, a genuinely large body. We found the largest one most recently. We found the whale before the minnows. And that is profoundly unlikely. Think about how detection works. Small objects are harder to find. They reflect less light. They're dimmer. Unless they pass very close to Earth, they're invisible. Large objects are easier to find. They're brighter. They stand out. So there's a detection bias built into our surveys. We're more likely to find large interstellar objects than small ones, all else being equal. That's fair. That's understood. But even accounting for that bias, the population statistics don't make sense. If we've found a 2.6 kilometer object among the first 3 detections, that implies the population of interstellar objects includes a substantial number of large bodies. And if large bodies are present, there should be vastly more small bodies. Hundreds, thousands, maybe more. Active comets are easier to detect than inactive ones. They glow. They shed gas and dust. They develop comas and tails that make them bright and obvious. An inert interstellar rock passing through the solar system might be completely invisible unless it happens to pass very close to Earth and reflects enough sunlight for us to notice. Oumuamua was inert, or nearly so. It showed no signs of outgassing, no coma, no tail. We only spotted it because it passed relatively close, and because Pan-STARRS, the survey that discovered it, happened to be looking in the right direction at the right time. If it had passed a month earlier or later, we would have missed it. That's the detection bias argument. We've probably missed thousands of small, inactive interstellar objects because they don't announce themselves. They drift through the solar system in silence, invisible against the background stars. Fair enough. But even accounting for that, finding a 2.6 kilometer object among the first 3 detections is strange. Population estimates, based on the detection rate and assumptions about survey completeness, suggest that at least one 3 eye-sized object exists within 4.5 astronomical units of the Sun at any given time. 4.5 astronomical units is roughly the distance from the Sun to Jupiter. That's a large volume, but it's not infinite. If there's always one large interstellar object that close, then the population density is substantial. That's comforting if you're trying to explain why we found 3I Atlas. It's not a fluke. The object was there because objects like it are always there. But it's unsettling if you think about what it implies. How many passed through the solar system before we had the technology to spot them? How many sailed through in the 18th century, the 19th century, the early 20th century, completely unnoticed because we lacked telescopes sensitive enough to see them? How many are passing through right now, too faint or too far to register on our surveys? How many will pass through in the next century that we'll still miss despite our improving technology? The uncomfortable options are these. Either our surveys are missing most interstellar objects, which means the population is far larger and more diverse than we realize, and our census is catastrophically incomplete. Or the size distribution is not what we expect, which means our assumptions about how planetary systems eject material are wrong, and the power law we rely on doesn't apply. Both possibilities are bad. Both suggest we're operating with incomplete information, making predictions based on assumptions that might not hold. And both tie back to 3I Atlas, a large mass, a strong acceleration that doesn't match the mass, odd chemistry, backward methane, industrial metal ratios. Each piece of evidence points to something unusual. And now, the statistics say, this object shouldn't have been our 3rd detection. It should have been our 100th. It should have been preceded by dozens of smaller objects, giving us a baseline, a population framework. Instead, we jumped straight to the large end of the distribution. Either our census is broken, or our assumptions are. And 3I Atlas isn't the only thing challenging astronomy right now. 2025 and 2026 have been strange years for astrophysics. While 3I Atlas was baffling comet scientists, while researchers were struggling to reconcile its mass with its motion and its chemistry, other corners of the field were grappling with their own anomalies. Exoplanet cores turning out denser than models predicted, with internal pressures and compositions that don't match formation theories. Stellar mass ejections happening earlier in star formation than theory allowed, with protostars launching material before they should have enough energy. Non-thermal chemistry detected in regions of space that should be too cold for reactions to occur, with molecules forming in environments where kinetic energy is effectively zero. Gamma-ray bursts with spectral features that don't match any known mechanism. Galaxy rotation curves that still resist dark matter models. Fast radio bursts with repetition patterns that defy categorization. Each anomaly, taken in isolation, is manageable. Science adjusts. Models improve. You add a new parameter. You refine a mechanism. You collect more data. That's how progress works. But step back and look at the pattern. Look at the sheer number of unexplained observations accumulating, and something more fundamental appears to be happening. Astrophysics is hitting boundary conditions. The models we've built, the frameworks we rely on, the equations we trust, were constructed from data gathered almost entirely within our solar system, or from observations of objects similar to those in our solar system. We've extrapolated those models outward, assuming they apply universally. And in many cases they do. Physics doesn't change from star to star. Gravity works the same in every galaxy. Chemistry doesn't rewire itself in interstellar space. The fundamental constants, the speed of light, the gravitational constant, the charge of an electron, those are truly universal. But the conditions, the starting materials, the evolutionary pathways, those can vary wildly. 3I Atlas is the first object we've studied in detail that formed entirely outside our solar system. Everything else we've observed, every comet and asteroid and planet, every meteorite that's fallen to Earth, condensed from the same primordial cloud 4.6 billion years ago. They share a chemical heritage. They share a thermal history. They share a formation environment. The solar nebula, the disk of gas and dust that collapsed to form the sun and planets, had a specific composition, a specific temperature profile, a specific set of physical conditions. Everything that formed from it carries that signature. 3I Atlas does not. It came from somewhere else. It formed under different conditions, around a different star, in a different nebula, with a different composition. It evolved in isolation for billions of years, never interacting with solar system material. And maybe, just maybe, that's why it looks so strange. This is not an excuse. This is not hand-waving. This is not saying it's alien, so anything goes. This is a hypothesis. If objects from other star systems form under conditions we haven't sampled, then they might not behave the way our models predict. The nickel-to-iron ratio might be normal for wherever 3I Atlas came from. The methane storage might be standard. The density might be typical. We don't know because we've only studied 3 interstellar objects, and 2 of them barely gave us any data. Oumuamua tumbled away before we could study it properly. 2 I/Borisov gave us some spectroscopy, but fragmented before we could measure its nucleus. 3I Atlas is the first one we've truly characterized. Our sample size is pathetic. It's statistically meaningless. But there's a darker interpretation, a possibility that makes scientists deeply uncomfortable. What if 3I Atlas isn't weird? What if it's normal elsewhere, and we're the outliers? What if solar system comets, the ones we've studied for centuries, the ones that form the basis of all our models, are the exception, not the rule? What if our entire understanding of cometary composition and behavior is based on a biased sample, and the universe is far more diverse than we've allowed ourselves to imagine? That possibility is thrilling. It opens up entire new avenues of research. It suggests that every interstellar visitor will teach us something fundamentally new. It's also terrifying, because it means we know far less than we thought we did. It means our confidence was premature. It means the models we've trusted for decades might only apply locally, in our tiny corner of one galaxy among trillions. And that brings us to the only honest conclusion. Let's review everything we know. Every anomaly, every contradiction, every piece of evidence that refuses to align. The nucleus is 27 times more massive than predicted, a measurement supported by multiple independent observations from both Hubble and calculations based on outgassing dynamics. The motion doesn't match the mass, with the object accelerating as if it's light while shining as if it's heavy, defying the fundamental relationship between force, mass, and acceleration. Methane is appearing when it should be gone, increasing post-perihelion in defiance of thermodynamic expectations and every sublimation model we've ever built. The nickel-to-iron ratio has no natural precedent, falling outside the range of every solar system comet we've ever measured, resembling instead the signatures of industrial metallurgy. And the statistics say we shouldn't have found this object at all, not as the third interstellar detection, not without finding dozens of smaller objects first, not without building a proper size-frequency distribution. Each anomaly can be explained individually. Measurement errors happen, calibration drifts, instrumental artifacts appear. Unusual thermal processes can alter sublimation sequences. Rare compositions exist somewhere in the universe. Detection bias skews our sample toward large active objects, but together they resist closure. Together, they form a picture that refuses to come into focus no matter how hard you stare at it, no matter which angle you approach it from, no matter how many different frameworks you try to apply. It's like looking at an optical illusion that never resolves, that keeps shifting between interpretations without ever settling into a single coherent image. Avi Loeb, the Harvard astronomer who made headlines for suggesting Oumuamua might be artificial, who has never been afraid of controversial ideas, who thrives in the uncomfortable space where data meets speculation, once described interstellar objects as blind dates from other worlds. It's a good metaphor. It captures the unpredictability, the surprise, the fundamental lack of control we have over the process. We don't get to choose what arrives. We don't get to prepare. We don't get to send a questionnaire ahead, asking what to expect. We don't get to request specific types of objects for study, objects that fit neatly into our existing frameworks and confirm our theories. The universe sends us whatever it sends, and we do our best to understand it with the tools and knowledge we have, however inadequate those tools might prove to be. But 3i Atlas wasn't a date. It was a mirror. It showed us the edges of our knowledge, the boundaries beyond which our understanding becomes speculative rather than empirical. It exposed the assumptions we didn't know we were making, the baseline expectations built from studying only solar system objects, the unconscious biases embedded in every model and framework. It revealed how much of our confidence was built on extrapolation rather than evidence, on local experience rather than universal truth, on the assumption that what we see nearby represents what exists everywhere. We thought we understood comets because we'd studied hundreds of them. But all those hundreds came from the same stellar nursery, the same primordial cloud, the same chemical heritage. 3i Atlas came from somewhere else entirely. 3 objects is not a population. 3 objects is barely a sample. You can't build statistics on 3 data points. You can't identify trends or patterns. You can't distinguish between outliers and norms with any confidence. You can't separate signal from noise when the noise might actually be the signal. Every interstellar object we detect teaches us something new, but the lessons are fragmentary, disconnected, isolated. We're trying to reconstruct an entire ecosystem from 3 fossils, trying to understand biodiversity from 3 specimens collected at random. We're trying to understand galactic diversity, the full range of planetary system compositions, and formation histories across hundreds of billions of stars, from 3 visitors that happen to pass close enough for us to notice. It's absurd when you step back and think about it. and yet it's all we have. We work with what the universe gives us, and right now it's given us 3 objects that don't fit together, that don't form a coherent narrative, that don't resolve into a simple explanation or a satisfying pattern. Skepticism cuts both ways, and this is something we need to remember as we grapple with 3I Atlas and its implications. We should be skeptical of extraordinary claims. We should demand extraordinary evidence before accepting radical revisions to our understanding. We should not jump to conclusions based on limited data, however tempting those conclusions might be. But we should also be skeptical of our own certainty, our own models, our own assumptions about how the universe works. When an object doesn't fit our models, the default assumption in science is often that the object is rare, unusual, a statistical fluke, an outlier, an exception, something that can be safely set aside, bracketed, ignored while we focus on the main population and the objects that do behave as expected. But what if the model is the fluke? What if our solar system, with its particular composition and formation history, with its specific ratios of elements and its particular thermal evolution, is the outlier? What if the comets we've studied for centuries, the objects that form the empirical foundation of all our theories, are not representative of comets in general, but only of comets from this one stellar system? What if we've been building universal theories from provincial data, extrapolating local patterns across the entire galaxy without realizing the limitations of our sample? We don't know. We can't know. Not yet. Not with 3 objects. But the possibility should give us pause. It should make us question every assumption we've taken for granted. So we're left with an unresolved fork in the intellectual road, a fundamental uncertainty that can't be resolved with current data. Is 3I Atlas a rare outlier, a 1 in a million interstellar wanderer that happened to pass through our neighborhood with a bizarre combination of properties that will never be repeated? A cosmic jackpot of strangeness that tells us nothing about the broader population? Or is it a signal of broader diversity, a hint that the universe is stranger and more varied than our parochial experience suggests? That what seems anomalous to us is actually normal elsewhere? Both are possible. Both are consistent with the limited evidence we have. Neither is provable. Not with 3 objects. Not with our current data. We need more visitors. We need better instruments capable of detecting fainter, more distant objects. We need surveys that can detect smaller objects, the 100-meter bodies that should vastly outnumber the kilometer-scale ones. We need spectroscopy that can characterize chemistry in real time, tracking compositional changes as objects approach and recede from the sun. We need time, patience, and resources. We need a larger sample before we can draw firm conclusions about anything. But here's what we do know. The one thing that's absolutely certain, regardless of how 3I Atlas ultimately fits into the larger picture: the universe didn't break our models. It exposed their limits. Models are tools, not truths. They're approximations, mathematical constructs built on the best data available at the time. They're simplifications of reality, designed to capture the essential physics while ignoring the messy details, the second-order effects, the edge cases. They work within their domain of validity, the parameter space, where they've been tested and verified. But when new data arrives that doesn't fit, when observations fall outside the model's range, when an object behaves in ways the equations don't predict, the model doesn't get to override reality. The model doesn't get veto power over observation. Reality wins. Always. Reality is the ultimate arbiter, and 3I Atlas is reality. It exists. It moved through our solar system. It outgassed. It carried methane and nickel and all the other anomalies we've cataloged. Those facts don't go away just because we can't explain them yet. The observations are what they are, independent of our ability to interpret them, independent of whether they fit our frameworks. Science progresses through discomfort. through anomalies, through the slow accumulation of data that refuses to behave, that doesn't fit neatly into existing frameworks, that forces us to question what we thought we knew. 3i Atlas is uncomfortable. It should be. Comfort is the enemy of discovery. When everything fits neatly into your models, when every observation confirms your predictions, when the data aligns perfectly with expectations, you're not learning. You're confirming. You're validating existing knowledge, which is useful, but not transformative. And confirmation, while satisfying, while reassuring, while psychologically pleasant, doesn't push the boundary. It doesn't expand knowledge. It doesn't force paradigm shifts. Anomalies push the boundary. They create the productive tension that drives science forward. They force us to ask better questions, to develop new frameworks, to consider possibilities we hadn't imagined, to venture into intellectual territory we've been avoiding. And right now, 3i Atlas is asking a very simple question. How much do we really know about what's out there? The answer, honestly, is not much. We've studied our own backyard in exquisite detail. We've cataloged the solar system with unprecedented precision. We've mapped the planets, discovered their moons, tracked thousands of asteroids and comets, characterized their orbits and compositions. We've identified patterns in how objects behave, how they evolve, how they interact. We've built frameworks that work beautifully for predicting solar system dynamics. We've achieved a kind of local mastery, a deep understanding of our immediate cosmic neighborhood that would have seemed miraculous to astronomers just a century ago. But the universe is not local. The universe is not our backyard. It's 93 billion light years across in the observable portion alone. And that's just what we can see from our particular vantage point in space-time. It contains 2 trillion galaxies, each with hundreds of billions of stars, many with their own planetary systems ejecting material into interstellar space. And we've studied exactly one planetary system in depth, ours. We've sampled one stellar neighborhood, one chemical heritage, one formation environment. 3i Atlas came from somewhere else. It survived a journey across light years of interstellar space, drifting through the void for millions or billions of years, weathering cosmic ray bombardment and micrometeorite impacts and the endless cold of the interstellar medium. It carried with it the chemical fingerprints of another world, another history, another set of conditions that we can barely imagine. And when we finally saw its core, when Hubble finally stripped away the coma and measured its mass, when Webb analyzed its composition and tracked its motion, it didn't match our expectations. Not because it was trying to deceive us, not because it was violating the laws of physics, but because our expectations were built on too narrow a foundation, on observations of objects that all share a common origin, that all condensed from the same molecular cloud 4.6 billion years ago. So what do we do now? We keep watching, we keep measuring, we keep building better telescopes and sharper models and more sophisticated theories. We wait for the next interstellar visitor, and the one after that, and the one after that. We slowly, painfully expand our sample size from 3 to 10 to 100 to 1,000. We look for patterns. We test hypotheses. We revise our frameworks as new data arrives. And maybe, eventually, we'll start to see the bigger picture. Maybe we'll understand what's normal and what's rare in the broader universe. Maybe 3i Atlas will make sense in a larger context, fitting into a population framework that we can't yet perceive, revealing itself as one point, in a distribution that becomes clear only when we have enough points to map. Or maybe it won't. Maybe it will remain an outlier, a singular anomaly that defies classification even after we've detected 100 interstellar objects, even after we've built a proper statistical sample. Maybe the universe is more chaotic, more diverse, more fundamentally strange than we're prepared to accept. Maybe every interstellar object will be its own mystery, irreducible to a general framework, each one carrying unique signatures from wildly different formation environments. We don't know. We can't know. And that uncertainty, as frustrating as it is, as unsatisfying as it feels, is also the point. Science isn't about having all the answers. It's about asking better questions. It's about pushing the boundary of knowledge, one observation at a time, one anomaly at a time. And 3i Atlas has given us plenty of questions. The universe didn't break our models. It exposed their limits. It showed us where our understanding ends and where mystery begins. And now, we get to decide what to do with that information. Whether to retreat into comfortable certainty or to embrace the discomfort and keep exploring.